Ladies and gentlemen, sorry to interrupt the chatter, but it's my great pleasure to welcome you all this evening to our first Your Manchester Insights lecture of this academic year. And it's wonderful to see such a full house. And indeed, we had people on the waiting list for this fascinating subject. I'd like to also give warm welcome to members of our Global Leadership Board who are here with us this evening. And later on, you'll hear closing remarks from the chair of our Global Leadership Board, Rory Brooks. So a few housekeeping notices as usual from me. So we're not expecting the fire alarm. So if it does sound, then it isn't a practice. There'll be lots of event ambassadors and staff to direct you out of the exits if that does occur. For tweeters, is that the right word? Tweeters in the room, then there are hashtags that will be on the screen. Please do tweet during the lecture and indeed afterwards and share what you learned tonight. And if I could just ask you to have your phones onto silent if you can. So this event takes place during World Space Week, which some of you may have read a little about. And that is an international celebration of all things space and science related to space and exploration. Tonight you're going to hear what I'm sure is a fascinating talk from one of our experts in this area. Before I introduce Professor Sarah Bridle, I'd also like you to give me a warm welcome for Tony Cross, who's here from the Manchester Astronomical Society, and he's just going to give you a couple of words about the Society and also about the Godley Observatory, which you may not be aware is in the Sackville Street building on the university campus. So Tony Cross, if I may hand over to you.
Hello, good evening, ladies and gentlemen. Thank you for that warm applause. The Godley Observatory. A lot of people may have heard of it, but there's a lot of people who've not heard of it. Godley Observatory is situated approximately 150 yards in the Sackville building. A generous gift to the citizens of Manchester in 1902 by Francis Godley, hence the name Godley Observatory. The Manchester Astronomical Society have been associated with the observatory on and off since that particular time, more so in more recent times from 1946, when we got full access to the observatory, and have been there every Thursday evening, 50 weeks of the year, for our weekly meetings. What can you see from the Godley Observatory? The wonders of the night sky. Think about it, Manchester, the city that's light polluted. But you can see all the solar system. You look through the telescopes, you see the mountains of the moon, the craters, the valleys, the sun rising, casting shadows, setting, casting shadows. Then you go out to the planet Mars, planet of war, red. During the seasonal changes, you can see the pole caps decreasing as they melt. You go out to Jupiter, the great red spot, a storm that's been raging for 400 years. You go out to Saturn, which has been in the news recently, with Cassini ending its 20-year mission. The planets beyond get a little bit more difficult to see. But from the Godley Observatory, you have got the wonder of the universe right on your doorstep. I always refer to the Godley Observatory as Manchester's gateway to the stars. And for those select few this evening who've managed to be picked out of all you attendees, they will be taken over for a guided tour of the observatory, the telescopes, and I believe the demand has been so great that we are in the process of organising an open evening where you'll be notified in due time, where you'll be most welcome to come and view the telescopes with a bit of luck. No clouds. You can also, with a bit of luck, observe the moon or whatever happens to be on display during the night. Also, during the day, we have facilities there to view the sun under strict control with special filters. I must say, you do not look at the sun unless you are looking professionally through a telescope. You'll see sunspots. you will see hydrogen alpha, that's the plasma you'll see on the television leaping off the sun. Stunning. I'm sure that our guest lecturer has seen and knows a little bit of all these things. So on that note, I will say thank you very much for giving us the time to listen, and for those guests, we will see you later on this evening. Thank you.
Thank you, Tony. So without further ado, it now gives me a great pleasure to introduce tonight's main speaker, Professor Sarah Bridle, who is a professor in astrophysics and has been at the university since 2013. And I'm looking forward to a wonderful adventure across the dark side of the universe. I hope you all enjoy. Sarah, please, thank you.
Thank you very much. Is this working? Can you hear me? Is this working? Testing. Is this microphone actually on at the back? You can hear me? Yeah. Fantastic. Okay, well, thank you all very much indeed for coming. I was getting into that. I could have just sat and listened to you for the whole hour. Okay, so I guess I should say something now. So I just wanted to find out a bit more about you, actually. So, yeah, to understand what kind of level to pitch this at. I mean, obviously, I've given this talk lots of times, so I know what I'm going to say. I'm more interested in what you want me to say. So I want to know, so hands up if you're a scientist. Okay, hands up if you feel like you've got no science background at all. Great. So we've got a wide range. Hands up if you're a physicist or astrophysicist. Just root you out early on, okay? Excellent. So I'm not talking to you. Okay, great. Also, just what do you already know about the dark side of the universe? So hands up if you've heard of dark matter. Great. Hands up if you've heard of dark energy. Great. Hands up if you know what the dark matter is. Very good, very good. I was hoping you'd know the answer and you could just tell me and then we could finish. Okay. Excellent. Okay, great. So I usually start this talk with, when we look at the night sky, what do we see? So I want to shout out a few things that we see when we look at the night sky. We just heard a good selection about our solar system. Anything anyone wants to shout out? Stars, yeah. Galaxies. Comets, great. Yeah. Satellites, yeah, very good. Excellent. Anything else? Milky Way, brilliant. I think we've got a lot of them. Excellent. I was giving this talk must have been about 3-4 years ago, and my son was in the back, age 4, and people were shouting out all these complicated things about, galaxies and the Milky Way. And then he shouts out, "The moon!" So proud of him. Taught you well. Anyway, so we see lots of things when we look at the sky. And I forgot to put the moon on this, of course. So there's lots of things we see. But of course, as you may be aware, since you've all heard of dark matter and dark energy, then this is just a small fraction of the total stuff in the universe. So we've got all these things that we can see. But then more interesting for this talk anyway is this thing which we call dark matter. So there's lots of theories in particle physics about what the dark matter might be, but we have no idea which theory is correct. Lots of candidates for the dark matter particles, and so that's maybe 20% of the universe roughly. But even more mysterious is this thing that we call dark energy, and there's lots and lots of theories about what the dark energy is. That's usually a sign that there's no good theory. Otherwise, we wouldn't be talking about tens of hundreds of theories. So there's really no explanation for what this is. And in fact, really, all we do is we see that the universe seems to be expanding faster and faster and faster. And we don't have an explanation for that. We could call it pink elephants. It's just something that we don't know what it is. The thing that is causing the universe to expand faster and faster. That's what dark energy means. I actually think it was actually quite an inspired choice of name, calling it dark energy, because actually a lot of the funding, or most of the funding for this work in the US at least, comes from the US Department of Energy. And I wonder if they think that we're going to be producing some sort of energy from this. I'm very sorry, just get this over with now, because I know there was a few people in the audience asking me about this earlier. There's no idea of how we could get energy from dark energy. Sorry about that, but just, the door's over there if you were waiting to find that. So this is what we see when we look at the expansion of the universe. We can see that it seems to be, this is sort of the size of the universe on this side here, and this is time along the bottom. So we see that the universe started off very small a long time ago, got bigger, and now it seems to be expanding faster and faster and faster. And so we kind of, what originally happened was that people thought, well, let's find out how much the universe is slowing down. So why were they looking at that? So I suppose if you had, I forgot to bring a prop actually. Well, I can get some sort of food. Ideally it would be an apple, but I've got this packet of crackers, which is basically broken anyway. So we throw something up in the air and we expect it to fall back down again under gravity. And everybody was expecting the same kind of thing with the universe. So you've got the Big Bang, and then you've got things expanding outwards for some reason from the Big Bang. And then they were trying to work out how much the gravity of the dark matter was pulling the universe back together again. They went out to find out, to measure this deceleration, this slowing down of the universe. And they got this completely surprising result, which was as surprising as if you threw up this into the air and it went shooting off into outer space. They found out the universe was expanding faster and faster, and there was no explanation for that involving the amount of dark matter in the universe, hence this idea of dark energy. And so this was awarded the Nobel Prize for the discovery of the accelerated expansion of the universe. Notice that that was for the discovery of the accelerated expansion of the universe, not for the discovery of dark energy, because we don't know what is causing this accelerated expansion. So the way that they used to find out about this dark energy was a method that we call standard candles. So supposing that you wanted to know about the this path here. So this is just a picture taken on Earth of a path, and what you can see here is lots of lamps. And so you might be interested to know about the shape of this, about how far away these lamps were, maybe compared to this one that you can measure nearby to you. And you might be able to look at these lamps and say, well, this lamp is smaller and fainter than this lamp here, so therefore it must be this much further away. So just this basic technique of looking at how bright and big different objects are, you can find out about how far things are away from us. So that is what they did, but they didn't use lamps. They used these things called type 1a supernovae. Okay, so what you can see here is just a cartoon of that. So we've got the Earth here, and imagine you had this type 1a supernova. So a type 1a supernova is where you've got a red giant star and a white dwarf star next to each other, and matter from the red giant star is dropping onto the white dwarf star. It's sort of falling off. Actually, must switch my phone off. You just reminded me. Just thought of that during the intro. It's off. Okay. So you've got matter coming off the red giant onto the white dwarf, and there's this theory that you'd expect a white dwarf to explode if the mass goes over a certain limit, basically roughly the mass of the sun. And so if you see this kind of supernova happening, you know the mass of that white dwarf when it exploded. And so what they did is they looked at these type 1a supernovae at all different distances and measured how fast the universe was expanding from looking at these distances and this red shift, this kind of Doppler shift type effect that you hear when an ambulance goes past, that you can measure from the spectra from looking at the colours of these supernovae. So they did that exact experiment, and they were trying to find out which of the blue, green or yellow curves we live on. So this yellow curve is an extreme case where there's a lot of matter in the universe, and we would predict that the universe expanded, reached a maximum size and then contracts again in the future, sometimes called the big crunch. And so the question was, where do we live? Do we live on this expanding forever line here, or do we live on a line which will eventually come back down and cause a big crunch? And so they found out they had to start putting this extra red line on, showing the universe accelerating in its expansion. Okay, so that's what this picture came up with that we must have lots of this weird stuff and lots of this stuff that acts like ordinary matter but is dark, and then we've got this ordinary matter here. So I hope you're a bit sceptical at this point. You know, I mean, it does seem a bit crazy that we've got these two invisible things that we need to put into the universe, and it might remind you of these epicycles they had to put in when they were trying to understand the motion of the planets, how the planets moved around the Earth, and they were trying to work out why the planets would be moving in these extra sort of these extra epicycles, they called them. And the story goes that then, you know, Copernicus thought, well, maybe they go around the sun, and everything became clear, that it all made sense. Of course, it wasn't quite that simple, but maybe that's what's going on here. Maybe we're having to invent new things, and there's actually some underlying fundamental problem with the theory of gravity, for example. And that's actually what motivates me to do this research, is because we really have no idea what's going on here, and there's a chance there might be something really that no one's ever thought of before. So that's what motivates me. But I want to now tell you a bit about how we can learn about this dark matter and dark energy from looking at the universe. Are there any questions on this so far? I prefer to hear your questions than just talk for the whole time. So any questions? Yeah. Mm-hmm. Great question. So the question is the amounts of dark matter and dark energy changing with time because the universe is expanding? So absolutely they do change with time. So in fact, early in the universe, then the universe was dominated by the dark matter. But as the universe stretches out, then the dark matter spreads out. And so the effect of the dark matter becomes less. Now, dark energy is completely counterintuitive. The dark energy, if you took a box of dark matter, okay, let's start with dark matter. If you took a box of dark matter and you stretch that box, then the dark matter would presumably spread out through that box. You'd have the same amount of dark matter in the box at the end, but it would be spread out more. So the density would have gone down. It's spread out more. Okay, take a box of dark energy, expand the box. You now have more dark energy than you started with. Makes no sense, okay? And in fact, in the simplest theories, the density, the amount it's spread out, stays constant as you expand the box. So if we think of the universe like a box, then we're stretching, the universe is stretching out as time goes on, and then the dark matter is spreading out, getting more spread out, but the dark energy, the density is staying about the same. And so eventually the dark energy becomes more important than the dark matter, and that's the theory of why we'd expect the acceleration to happen only recently. Great question. Any other questions? Yep.
You said earlier on, you said the universe seems to be expanding.
Yes.
I'm thinking that, again, it's similar to the autonomous cycles and that, but when we look at the world around us, we have physics and we know the way it works, but we know when we start to go at the micro level, it doesn't work quite the same anymore, and we have to tweak the rules of physics to make it fit the micro level.
Mm-hmm.
Could it be, since a lot of this is based on what happens a long, long, long way away, and the further away we seem to be looking, the worse it gets.
Mm-hmm.
The worse it gets, could it be that as we go further and further away, we assume that the laws of physics work the same over big distances as they do?
That's a great question. Yeah, absolutely. So we're assuming that we understand gravity. We're assuming Einstein's gravity when we do all these calculations. And actually, we've never tested gravity on those kind of scales, those kind of distances. So some of the theories, which don't work great, but they are, some of the theories that are being considered, is that maybe gravity leaks out of this 3 dimensions, and so is gravity actually weaker on when things are far apart from each other. So we just don't know, and I think the bottom line is that all these things I'm going to tell you about, they've been designed with the idea of finding out about this dark energy. But actually, they also would tell us if there was something wrong with the laws of physics as well. So I think that's the general motivation. Because we don't know what to look for, then we're looking for dark energy. But actually, any of these things would be very interesting to tell us about the difference between how things become clumpier with time, how things get stretched out with time. If you see differences between those two things, then that's a signature that it's not dark energy. It might be some sort of modified gravity.
It would be unfortunate if you spent a lot of time looking for something that isn't there.
Yeah, so I wouldn't be doing this if I wasn't confident that at least for some models of modified gravity, we would still find something even more interesting. Yeah, that's a good question. Yep.
How does dark energy relate to the superstrings theory?
Nobody knows. Yeah, so there's people trying to link the two, but one of the possibilities is. So in terms of string theory, then if you're talking about having lots of different models with different kinds of parameters, and this thing called a string landscape, which is absolutely not my area of expertise at all. But in these models, then you've got lots of different possibilities for what's in the universe. There's lots of different possible values for the amount of dark energy in the universe. And so one possibility is we happen to live in a universe which has exactly these values, but there's actually tons of other universes out there with all different values. We don't know. It's very hard to test that kind of theory, and some people get cross about whether that's really science if you can't test the theory. But anyway, it's important to think about these things, but that's about my limit on that, so no more. Yeah.
Right, so we have E equals mc squared.
Okay.
So when we have this dark matter that we can measure speeding up exponentially, does that not, according to that rule, explain increasing dark energy?
Yeah, so it makes absolutely no sense. Dark energy doesn't make sense at all. So yeah, it's you can talk about the equations, you can talk about the pressure and density of dark energy, and you can talk about how it would spread out. One possibility is maybe a quantum vacuum, so you've got particles appearing and disappearing, and this would have this kind of effect. So it's something that has an effect of pushing things apart, but it's not something that we can really have any physical intuition for.
So following on from that, if that's what's happening, this dark matter would be slowly going down each time we measure it. Is that the case?
Yeah, so the density of dark matter is going down as time goes on. Yeah, absolutely. Great, I'll take one more and then I guess I should tell you a bit more.
The units of this, it's the mass of these things you're talking about, isn't it? It all adds up to 100%, isn't it? 75 times 1
Yeah.
It's the mass.
It's the energy density that adds up to, so we're talking about the percentage of the energy density. So we would use E equals mc squared to convert from the mass of the dark matter into this equation. Yeah. Okay, great. Excellent questions. Fantastic that you're all awake. And you brought up some really good points there, which I'd forgotten to mention. So that was really, really fun. I'm going to tell you a bit about how we can measure. I've got no idea what time it is, by the way. Is there a... Oh, there is a clock. You can all see the time, but I can't see. I see. Right, fine. Okay. So I'm going to tell you a bit about how we can learn about the dark matter and the dark energy. Now, one time when I was giving one of these talks, I think it was an astronomical society, somebody in the audience said to me, why is it called dark matter? Shouldn't it be called transparent matter? And they're absolutely right. So dark matter, the definition of dark matter is that it doesn't interact with light. It's matter that does not interact with light in any way. And so actually that's what we mean when we say transparent. And in fact, we see transparent things all the time. So I'm going to now ask you, well, first of all, am I holding anything in my hand? Is there anything inside this glass? You all know, you see transparent things all the time. In fact, now I've got it here, I'm going to have some. It's thirsty. Right, okay, so you see transparent things all the time. And we use exactly the same equations for the way that light is affected by glass to do with the refractive index, as you can use exactly those same equations when we're talking about dark matter. And I'll show you in a moment a bit more about that. So we're going to use the bending of light by gravity to find out about the dark matter and the dark energy. I'm going to tell you a bit about how that works now. So if we had a big mass here, then you might have seen this picture before, that you might have a light ray going along here like this, and it would get bent by the curved space-time that's caused by this big mass. And so if we're sitting here, we see this light ray coming from this direction, and we think, oh, there's a star over there. So we would think it was over there. Now that's the simple version of that. But now, if we actually then have something more complicated, like a big clump of dark matter and maybe a galaxy right behind it, we would see the light maybe getting bent all the way round. Maybe that would come straight through the middle as well. What would we see as an observer if we were here? We've got a clump of dark matter there and then a very distant galaxy behind it. Does anybody picture what we can see there? Shout it out. Circle. Yeah, same thing several times, all the way around, making a circle. Exactly, yeah. Great. So, in fact, I am going to show just one equation in this whole talk. This is, when I was a third year undergraduate, then I went to my lectures and I said, I really want to do a summer project. Please can I do a summer project? And they said, well, you could do a summer project on gravitational lensing. And I said, no, I'm not doing that. Because this phenomenon. I'm not doing that. I haven't done general relativity yet. I need to study general relativity before I can do anything on gravitational lensing. It turns out the only thing you need to know from the whole of general relativity to do everything that I do in cosmology is this one equation, which honestly, I think you could probably actually have guessed. Okay, so this equation here says the amount that the light gets bent depends on the mass of the object. Okay, and not very surprisingly, the bigger the mass, the more the light gets bent. Seems reasonable. Okay. The other thing in this equation is this distance. So the closer the light ray goes to the object, then the more the light gets bent. Seems reasonable. So basically, if this distance is small, then this value will be large. So this b goes on the bottom of the equation. And that's really the physics that's in this equation. The rest are just physical constants. This factor of 4 is very famous because it's this factor of 4 that made the difference between Einstein's general relativity and a sort of back-of-the-envelope calculation you could do with Newtonian gravity. That was what made Einstein famous in the eclipse experiment 100 years ago. So this is the only equation I'm going to show you in this talk, and it's really just to say that this is all that's going on here. The light is getting bent depending on how massive the object is that the light is going past. So back to some pretty pictures. So you just shouted out that you would see a circle. That's right. So if you had light coming out of this object here, it'd get bent round here, and then we would imagine the light was coming from over here. But the same thing would happen all directions, all the way around this, and we would think that the object was a circle over there. If the object was a little bit off-centre, then we might see 3 objects. And actually, it's exactly the same equations as refractive index from light. Now, I've got to say, don't do this at home, because otherwise you might sue me for using a candle. But if you did have a candle under close supervision from a health and safety inspector, then you could maybe get a wine glass and then hold it up and look at that candle, and you would see exactly the same kind of shapes that we see in the universe due to this gravitational lensing effect. So here you can see this beautiful thing. It's called an Einstein ring, because Einstein was the first person to realise that you would actually see a ring if you had this configuration. You can see multiple images sort of stretched out. You can see maybe 3 images there, but they're kind of stretched out. So you can play around with don't play around with that. But this is some, maybe you can just about see here, some pictures of, these are galaxies. These are pictures taken in the universe. So you can see here an example of a distant blue galaxy, an example here of a red galaxy in the middle. And if you've got very good eyesight, you might be able to see these blue arcs around the outside. There's a few on there. And there's 4 images on that one as well over there. So these are images we've seen in the sky. And this is arguably the most beautiful image that's ever been taken of gravitational lensing. If you look at this picture and you know what you're looking for, you can start to see lots of very distorted galaxies. Can anyone see any distorted galaxies? You can nod vigorously if you can, or put your hands up if you can see some. It's quite hard on this particular screen, I think, but yeah, if you can sort of wave your arm in the general direction where you think you can see them. Yeah, I like to see lots of fingers waving about, really. Yeah, okay, that's great. So you're probably pointing at this one maybe here. Yeah, and there's one down here as well. These ones out over here as well. And in fact, if you download this, if you type into Google A2218, then this is the telephone number of this cluster of galaxies, and you can see hundreds of galaxies which are stretched out, elongated around this central cluster of galaxies. And we can use this effect to tell us about the mass of this cluster of galaxies. In fact, there's a lot more information in here which I'm going to talk about in a moment. First, I'm going to show you, ideally, we would be able to do this experiment where we would take some distant galaxies, which are the blue ones, and we would move them along. That would be great because then we could see a movie like this where we've got maybe a cluster of galaxies here, the red galaxies are the old galaxies in the cluster, and we'd see how the background galaxies would change if we could move them. Unfortunately, can't move them, but this is what you would see if you could. So that's just to illustrate the kind of effect that's going on. Now, this is all very beautiful, but there's very few objects in the universe that look like that are this dramatic. But every single galaxy in the universe is distorted very slightly, or its image is distorted very slightly due to this kind of effect. And so I'm interested in galaxies like this one down here that you can't even see, which is very, very slightly distorted. And we can use those galaxies to tell us about the mass distribution in the whole universe, make a map of the dark matter in the whole universe. Okay, so you want to play at home. This is a picture of me a couple of years ago in my youth. And if you take this app on your iPhone, you can then distort your friends or your enemies. Hours of fun to be had there. Now, this is the kind of picture that is more relevant to what I'm going to talk about. So can you see anything between us and the tree? Hopefully you can all see that there's something in the way, which is this bathroom window. And this is actually a bit more similar to the kind of situation that we've got in the universe. So in the universe, our simulations tell us that we've got dark matter distributed a bit like this. And the dark matter is like this, a bit like the glass, analogous to the glass in the bathroom window. So we're looking at distant galaxies which get distorted by this dark matter. Any questions on that so far? How big's the Milky Way on this? On this kind of picture here, for example?
That one you were showing us, the one that was on the screen.
Oh, sorry, yeah, got you. Good, yeah, very good question. Yeah, so this is a massive cluster of galaxies. So the Milky Way would be something like one of these kind of little tiny white specks here. Yeah. I mean, this is a simulation, obviously, so it's not in here, but that would be what the kind of size. Yeah, good question. Any other questions? That's fine. You want to know what that picture was that I flashed up and then didn't show you out. Okay, in my dreams, the sky would look like this. Okay, this would be very convenient if we wanted to know how much galaxies were distorted by the dark matter. It would be very convenient if they were all circular and on a grid. Because then, if there was dark matter between us and those galaxies, then it would get distorted in a way that we could then use to invert and find out about the distribution of dark matter, which is this in this simulation. So you might be able to see that some of these galaxies are getting distorted around something there. There's a clump a big clump of mass there, and you can spend hours looking at this and inverting it in your head. And obviously, we can do that in the computer as well to make a map of the dark matter. This is a different way of thinking about how we can learn about the dark matter from shapes of galaxies. So if you had two, I actually think this looks a bit more like a picture out of a biology textbook. It's not exactly correct, it's more of an artist's impression, but it gives you the general idea that if you had two galaxies which are fairly close to each other, then they would travel through this web of dark matter, and they would get distorted in roughly the same direction because they've both travel past a similar dark matter distribution. And these two galaxies over here would both be distorted by the dark matter over here and might be both stretched in the same direction as each other. So we get these kind of clues as to the existence of dark matter, but it's very, very difficult to then invert that to find out about the distribution of dark matter. Any questions on that? Yep. Very good. Excellent. Yeah, we don't. Yeah. So this is the basic problem that we have. That's exactly why I would rather they were all circular, to be honest with you. But yeah, if we look at one galaxy, we don't know whether it's been stretched or whether it looked like that in the first place. So what we can do is we can look at, for example, pairs of galaxies and see, on average, are pairs of galaxies pointing in the same direction as each other or not? So that's a kind of statistical way of phrasing it. Another way of phrasing it is to say, if we look at a load of galaxies, in fact, I've got a picture of that, I think, on my hidden slides, which I could show you now. If we've got, I'm going to be brave and just see if I can show you that. Oh, it's disappeared. Where's it gone? Oh no, it's so hidden that I can't show it to you. Okay. Oh no, there it was. There it is. Look, there it is. I can see it. Okay. Okay. So imagine that you had lots of galaxies, all in the similar patch of sky, and if you average together the shapes somehow, you might expect on average the galaxies would be pointing in random directions. You might not. But supposing they were, then you would on average get a circle if you averaged all the shapes together. Now if they were all squashed in the same direction because of the dark matter, then when you average them together, you'll get something pointing in that direction that they were squashed in. So that's another way of thinking about the same thing. So it's a very statistical kind of, we have to have a million galaxies to see this effect at all. Do you believe it? See if I can figure out how to put this on play again. Okay. Any other questions on that? Cool. Okay. So you might be asking, I thought this was about dark energy. She's not talked about dark energy yet. So I'm now going to tell you something which still to me sounds ridiculous, that the method with the most potential to tell us about dark energy is to look at dark matter. So we're looking at one invisible thing to tell us about another invisible thing, which even as I say it, I do feel that it does sound a bit improbable, but you do the calculations and it's very difficult to measure the dark energy basically. And so how does that work? So what we do is if we look at the distribution of dark matter at different times in the history of the universe, then that responds to dark energy. So in the simulations, the universe very early on looked like this, and gradually the dark matter clumps together and ends up in that picture that I showed you in the first place. So as we look back in time, the dark matter is getting clumpier and clumpier. So what's happening is that the gravity is pulling clumps of dark matter together. At the same time, the universe is expanding. So if the dark energy is expanding the universe faster and faster, that slows down this clumping process. And so if we can look at the dark matter clumpiness at different times in the history of the universe, it will tell us about the expansion rate of the universe and therefore about dark energy. It works, but it's really, really hard to do. And now I'm going to tell you about how incredibly hard that is. Any questions about that particular concept before I move on? So I'm going to tell you about something even more crazy now. So this is a typical picture of the sky that we use to learn about dark matter and dark energy. So this is a typical star, and here's a typical galaxy. You can hardly see it. We're looking at the very faintest galaxies that we can measure the shapes of. And of course the telescope distorts the image as well. So you've got lenses in this telescope and maybe reflections which are all causing the image to get distorted, and the atmosphere is blurring out the image. So what we do is we look at stars which are so small they would appear as points if it was a perfect telescope, and we use those stars to understand the properties of the telescope because the telescope distorts the image more than the gravitational lensing effect we're trying to measure. So that's one thing we do, which makes it really hard. This is the gravitational lensing effect. So we've got a galaxy here, it gets stretched. That's the effect we're trying to measure. Now in this picture here, I've exaggerated it. It's actually about a factor of 10 less, typically, that a galaxy gets stretched, but I just wanted you to be able to see the stretching. Okay, so this is exaggerated. Then we have a blurring of the image due to the atmosphere, and the telescope is actually worse than this. Then we've got the the detectors, the camera that we're taking the photograph with, has these finite resolution pixels here. It's actually a bit worse than this. And then you've got the noise on the image. It's actually a bit worse than this. So overall, you're trying to measure an effect, which is a factor of 10 less than this, from images looking worse than this. And whenever I say this, again, I sort of feel like, yeah, maybe this is crazy. So typical galaxy that we're looking at to measure this gravitational lensing effect looks like this. And so we've got a sort of intrinsic shape of the galaxy, we've got the squashing due to this gravitational lensing effect, and then we've got the noise on the image, which is about a factor of 10 bigger than the effect we're trying to measure. And this is where it gets even worse. So we're trying to measure gravitational lensing in order to tell us about dark energy. The gravitational lensing effect is changed by dark energy by about 1%. So we have to measure this gravitational lensing effect, which is a factor of 10 smaller than the noise and the intrinsic shapes of the galaxies, to an accuracy of 1 in 100. Which is, so we need millions of galaxies to even see this gravitational lensing effect, and we're looking at hundreds of millions of galaxies to try to use this to find out about the dark energy. And so we need to be able to measure the shapes of these galaxies to such an incredible accuracy that we're not biasing that result, we're not getting the wrong answer for dark energy. And this has been done. This has been done with the Hubble Space Telescope. And this is a map of the dark matter that they made using this Hubble Space Telescope over just a square degree of the sky. So it's incredible that we can look at different galaxies at different distances from us and use that to make a three-dimensional map of the dark matter. Now, this is an artist's impression of the light travelling to us from a distant galaxy through that exact dark matter distribution that was measured. There's some issues with this. I'm looking for anybody that can spot the scientific inaccuracies, but that's the rough picture. Okay, so looking ahead, because this is such a powerful tool, there are lots of different projects planned to tell us about the dark energy and the dark matter. And so these projects are all, some of them are underway now. Over the next decade or so, these are going to tell us a lot more about the dark energy. They're costing typically hundreds of millions or billions in some case to do these projects. So this is, very much something that we want to tell you about and make sure you think they're a good idea, really, because if not, then we're wasting an awful lot of money. So you've come tonight, that's a good sign. This is the dark energy survey that I've been involved a lot in. I'm just going to speed up a bit, actually. So this is the telescope here that we're using for this project. Lots of pretty pictures of telescopes. You can look at these afterwards. This is the mount here. This is them trying to make the CCDs. So these are the camera. This is the detectors in the camera. They're putting these in. This is the full thing. Now it's been done. They made the filters in Japan, even though there was a tsunami. We thought it was going to be delayed, but no, they managed to produce these things before the deadline anyway. And then these are the lenses. This is one of the largest optical lenses that's ever been made, being inspected by my then colleague at UCL, Peter Dole. And it's a large collaboration. We have to go to places like, the beach near Barcelona every now and again for conferences. It's a hard life. And this is the timeline. So I've been working on this project since it started in 2003. And there's a very special time coming up now, which is in February. We'll finally have taken all the data for this project. And we're currently analysing the shapes of hundreds of millions of galaxies to be able to bring you the news about dark energy. For now, what we've done is we've analysed a small patch of sky, this green patch here, and this black area here. And we've made maps of the dark matter. We've also made lots of pretty pictures of galaxies, which you could again look at in your afterwards. Now, this is an exciting bit here. Okay, so here, this is very obvious to me after many years. This is a cluster of galaxies. It's sort of lots of red galaxies all close together. And we looked at this in detail because we expected there to be lots of dark matter near to these galaxies. And so we analysed the shapes of tens of thousands of galaxies near to here, and we made a map of the dark matter. This is the first map that we made of the dark matter using this project. And so you can see here contours showing you there's lots of dark matter just near to where these red galaxies are. So this is exactly what we expected. And you can see here the distribution in black of the positions of the galaxies relative to the dark matter. So we see that galaxies tend to live where there's lots of dark matter, which is what we expected, but it's kind of cool. Now if we zoom out a bit, we then made this map, which is the largest ever contiguous map of the dark matter in the universe. And what we're currently doing is we're doing that over a much larger area now. We're looking at, that was for this green area here, and we're now looking at the whole sky of this, in this red area here. It's just a coincidence, it looks like a tank. It's not deliberate. There's lots of other there's lots of other data over here, and this is where we wanted a sort of roughly circular thing, and then when the sky comes up, it's in Chile at the time we had the telescope, it comes up over here. So this is the patch of sky we're looking at. We're trying to make a map of the dark matter, not covering this green area that I just showed you, but covering this entire red area that we're working on now. So it's a really exciting time for us. Looking even further ahead, I've been involved in getting the UK in this project called the Large Synoptic Survey Telescope, the premier ground-based optical imaging survey of the next decade. And this is going to be taking, it's really a big data project, hundreds of petabytes of data, 20 terabytes a night, taking 800 images, like a movie really, of the whole southern hemisphere every 3 to 5 nights. It's an artist's impression of what it'll look like. It's very advanced technology, no supports for the lenses. No, that's not really true. It's just an artist's impression. Again, it's definitely going to look exactly like this. Yeah, we're not really going to see the universe reflected in the lens of the camera, but it looks pretty. They've blown the top off the mountain, so it's definitely happening. And they're working hard now on getting the telescope up on the mountain, and they're making the primary and secondary mirrors. So, so which pictures? Yeah, sure. Yeah, this one here. Let me see if I can actually remember. So it's got a 10 square metre collecting area. So this must be about 3 metres across. So I'm going a bit blank here, but that seems about right. Yeah, any other questions? Yeah. I'm conscious I should probably wrap up and then you can ask lots of questions. Okay, so I'm nearly done. Okay, so that's basically it. So we're looking ahead for all these future telescopes. The Square Kilometre Array, of course, is led out of Manchester. It's going to also look at dark energy and dark matter over a slightly longer time scale with incredible precision. And then Euclid satellite is going to try and do the same thing, coupling in with the measurements that we can make on the ground. And then the Dark Energy Survey, look out in the news, hopefully in the next year or two, at our final results from the Dark Energy Survey. And you never know, we might be finding something out about whether we've got too many epicycles here and we've got a whole new theory to worry about. So thank you very much indeed. Thanks for all your fantastic questions.
We still have time for a few more questions, if anyone has some more. Yeah.
Is all the research done with visible light, or are you doing anything with longer and shorter wavelengths?
It's a great question, yeah. So is all the research done with visible light? Yeah, so we're actually, all my research is done with visible light. So gravitational lensing is exactly the same at all wavelengths. So there's no reason why we shouldn't be able to look at these pictures in the radio. And indeed, the very first Einstein ring was observed by astronomers at Jodrell. So this is something that was done in the radio. So you can do it in the radio. It turns out that just because of the history of detector development, that you do get more galaxies in the optical, which is what we need. So the Square Kilometre Array will actually overtake in the future, but at the moment with the current telescopes, that optical is the most powerful way to do this.
Question down here.
Does dark matter contain dark energy, or are they two separate?
Okay, does dark matter contain dark energy? So no one really has a clue what either of them are, so it's quite possible. There are some theories in which dark matter turns into dark energy as time goes on. So we don't know. The simplest theories, they are different things. So if you take the theories of what dark matter might be, then they would be some sort of particle, which is one of the many particles predicted by particle physics. So then there would be something completely separate needed in order to explain the accelerated expansion of the universe. But no one knows.
We have a question in the middle.
Can you not speculate just in a minute at some of the candidates for dark energy, some of the particles that could be the candidates?
So particles tend to, yeah, so can I speculate about what might the dark energy be? So, there's lots of ideas about, so vacuum energy is the simplest theory. So the idea is that particles appear and disappear in a vacuum. And the only problem with that theory is that the amount of dark energy that it predicts is 10 to the power 120, so 1 followed by 120 zeros, bigger than the amount of dark energy that we see. So this is often referred to as the biggest, discrepancy in physics. And so there must be something wrong with that theory. And the simplest approach is just to say there's some cancellation, which means that is zero, that effect. But of course, who knows? So that's one of the possible theories. I think the most exciting theories are modified gravity. So when we're looking at maybe gravity has a different effect if you're far away than what we expect from Einstein's general relativity. That's the most exciting thing for me. But there's other theories in terms of scalar fields, which is a mathematical construct about what the universe is made of. So that's the kind of thing that people are talking about. But literally there's a list of hundreds of possible theories which are all being discussed because there's really not a good one. They've all got problems with them.
Talk about the universe expanding, then slowing down, then speeding up. Where? Because we are looking at it now, aren't we? So presumably, if we make a measurement now, that's what we see.
Good.
Now, if you're looking back,
How do we know about the past of the... Yeah. Yeah.
The further back we look,
Yeah.
the smaller the universe was, in a sense, you can expect certain conditions to apply. And now we're in the expanded portion.
Okay.
Then.
So yeah.
Very simplistic. I mean, if gravity is applied to small, we would expect it, as from the equation you had, that the distance, the gravity was stronger. As you look at it now, once it's bigger, then the gravity will be less. So, have we not just simply
Okay. So.
making wrong judgments on measurements?
Okay, yeah, so that's a good question. So there's two issues there, I think. So one issue is, when we do the predictions, we do take into account that there was more dark matter was more dense in the past than in the present. So that's already in the predictions. But there's one really important thing I forgot to say, which is, how do we look back in time? So, great. So I'm glad you brought that up. So basically, when we look at distant galaxies, then, of course, as you know, light takes time to reach us. So if we look at the sun, well, don't look at the sun, of course, don't look at the sun, yeah. If we were to look at the sun without a telescope, then the light has taken 8 minutes to reach us from the sun. So we're looking at the sun 8 minutes ago. So when we look back in time at the kind of galaxies that I'm talking about here, the galaxies emitted that light when the universe was half its present age, typically. So when we're looking far away, we're also looking back in time, and so that is how we're able to look at the clumpiness of the universe when the universe is about half its present age, and then if we look more nearby galaxies, we're looking at the clumpiness of the universe closer to today. So that's how we learn about the history of the universe.
Thank you very much, Sarah. We've run out of time. I just want to ask those with confirmed places on the Godley Observatory tour to meet at the reception desk in the foyer, please, after the event. Now I'd like to introduce Dr. Rory Brooks, Chair of the Global Leadership Board, to close the event.
Well, good evening, everybody. That is an impossible act to follow. And speaking for myself, I don't think that in such a short space of time I have been so fascinated, so informed and so confused all at once. Is there anybody else out there who feels the same way? I presume you can call that success. So can we please have a huge round of applause, please?
Thank you. Thank you very much. Thank you.
I only have one question. If you met dark matter, could you bump into it?
No.
Oh, right, okay. So we're not going to suffer from that, okay, too much. I have the great privilege of being chairman of the University of Manchester's Global Leadership Board. And I just thought I'd explain for a minute what we do. Basically, our job is to support the philanthropic development of the university and to improve its philanthropic income as the university, like all good universities, attempts to diversify its various sources of income. And in doing that, we act as support to the senior management of the university, to the president, Nancy Rothwell, to the registrar, Will Spinks, and if I can find Kate wherever you are, to Kate White, who runs a division for development and alumni relations. And these are critical people to the university because philanthropic income to the university has increased from very modest, it hasn't expanded at quite the rate of the universe, but we are working on it, aren't we, Kate? Yes. To a not insubstantial number in the 20s of millions per annum, with the view that that will continue to increase and no doubt accelerate beyond its current levels. The point is that the vast majority of income that the university attracts is given to very defined purposes. And so the philanthropic income, although it's not a huge number in the context of an institution whose turnover is over £1 billion, the fact is it does constitute an important amount of the discretionary and disposable income for the university to do the things that it otherwise could not do with its standard income. So this role is increasingly important, and our other role is to make sure that there is continued and expanded engagement by all people who are stakeholders in one form or another in the university. One of the standard expressions about this great university is that it is both local and global. And I think we can add this evening that it is local, global, and cosmic, as the expression we would use. This university is obviously an extremely integrated and important part of the city of Manchester and of the Northwest. But it is also true, as the President has found out as she's toured around the world, a lot of which she's been to even quite recently, that what this university does has resonance around the world, be it for cancer, be it for graphene, be it for various human inequalities, or various other of the beacon areas in which it does learning and research. And one of the other areas that the university is getting global recognition for is that we don't just have two primary goals, which are clearly learning and research, but three primary goals: learning, research, and social responsibility. And taking the third element, social responsibility, up to the level of importance that is held by the other two posts is garnering international and global recognition. I have to say that I last was in this room in 1975. And I thought that when I left university that this might be the last time I ever saw it. And there was no reason to expect that there would be an engagement between myself as an about-to-be graduate and the university in my later life. And I now realize that that was going to be missing a fantastic trick in my life, and that the university was an inherent and integral part of the social capital that makes me me. And I have to say I have been a huge beneficiary of re-engaging with the university, and I'd like to convey that message to everybody in this room. And it doesn't matter what your form of engagement is, whether you are a student, whether you used to be a student, whether you have worked here, whether you do work here, whether you're just a neighbour of the university, or you travelled from somewhere deep in space to attend this lecture. Engagement takes many forms and parts. Manchester University is not alone in being one of a class of institutions called universities that I still think are one of the great unheralded assets of our country. And I have to say it's a privilege to be part of this community, and I urge you all, in whatever form you think is appropriate, to engage with the university and join us in that community. So thank you very much. Well, I think now that there is some light and dark matter out there. The light white matter is white wine, the dark matter is red wine. I'd like to conclude by thanking you for your attendance and a last round of applause. Thank you.